Head porting. Now that we have a block with a stroker in it, now we can go and we can maximize the cylinder head. Back when I had my speed shop, I got to play and experiment and try a lot of different theories to see how they worked in the real world. I got to bring one guy up. Dez was his username, down in South Florida. He had a 1989 Chrysler LeBaron, 2.5 turbo, which from the factory is 156 horsepower. Had a 3-speed automatic, no overdrive. Now, once a month, he would have to go from Miami to Jacksonville and back for work. And on that trip, he would drive 80 miles an hour. That's the flow of traffic there. And he would get about 24, 26 miles per gallon on that once a month trip. Well, he decided he wanted to just totally revamp this whole package. I ported the top end, his head, intake, and exhaust manifolds. He followed a well-used recipe that included a bigger turbo, a big intercooler, these injectors, that computer tune, and the recipe, if you used a stock top end, delivered 265 horsepower. If you follow the recipe, 265 horsepower. But then they added, if you get a ported top end, you'll get more. In fact, they said, we have seen as much as 360 horsepower out of this. So Des followed the package. I ported his top end. And the only reason I bring this up is because he showed me dyno sheets. I wish I would have kept the email transmissions. 430 horsepower. That's 70 horsepower more than the second best guy. Oh. And on his trips from south to north, South Florida again once a month, he went from mid-20s to low 40s. 42, 43 miles per gallon, 80 miles. Wow. The cylinder head is probably the single most important part of the whole engine. I mean, if you think about it, the air-fuel charge coming in, does it swirl, does it vaporize, or does it puddle and run? Well, that's up to the cylinder head. Once it gets past that intake valve, is it going to just fall to the floor, or is it going to swirl around and homogenize? The cylinder head will tell. On the compression stroke, are we going to cause detonation on fuel, or can we run really cheap fuel with high compression ratio? The cylinder head has a lot to do with that. Once the spark plug fires, what's going to happen to that air-fuel charge? Is it going to explode and cause detonation and break parts? Is it just going to kind of sort of put forth a milquetoast effort to get some energy out of the fuel? Or is it going to work diligently to extract massive amounts of power from that fuel? Again, cylinder head. And then when we're done, we got to get rid of all that exhaust, and it's got to go through the exhaust valve through the cylinder head. Literally, the cylinder head is the mastermind. It is the limiting factor when it comes to just how much power you can make and how efficiently you can make that power. For head porting, we're dealing with a fluid. It's air, it's fuel, it's an aerosol. But if you study a stream and you watch how when it necks down, everything speeds up, and then when it opens out again, stuff that was floating will fall to the bottom. You'll have little rocks and eddies, and just watch how the water tries to get around sharp edges. Just by watching a stream, you can learn where the air wants to go in your cylinder head. You're going to need some basic tools. If you have an air compressor, Harbor Freight sells a pneumatic grinder, $30 or less. Comes with 5 stones. There's electric grinders. Eastwood has them. There's some pretty fancy ones. And then you got your bits. You got your short shank, long shank. If you look at the image there, the iron heads have a fine flute. The aluminum heads have a coarse flute. And you don't want to use the wrong one on your head. So if you're working with cast iron cylinder heads, make sure it's the fine flute. And then you get your sanding rolls. There's a bureau. It goes into your grinder, and then you have your rolls which spin onto the stem. And then you can go in there and you can smooth over coarse areas. Sanding rolls come starting probably around 30 grit on the coarse side. Typically around 220 is your high-end standard for a smooth surface, although specialty houses like McMaster-Carr, you can get them, 600 grit to create a mirror image on your surface. Our goal here is to get the air-fuel charge coming in through the intake valve and swirl around in the cylinder. By biasing the port, we want the flow to come in at the tangent. The tangent would be the outside of the circle. David Bizard, in his videos, does port biasing, but he guides everything to the center of the cylinder because he's looking to just get it in there, volumetric efficiency. So biasing the port to the center of the cylinder will give you better volumetric efficiency at wide open throttle, 7,000 RPMs. But for fuel economy, we want to do it backwards. We want to bias outwards so that as it comes out, it hits that cylinder and just curves right around. And it keeps spinning. And that's your homogenization. That's what blends the air and the fuel charge. One of the ways that we can do this and still keep the ports relatively small for velocity is to use epoxy. And you can have a liquid epoxy like the 2-part JB weld. You mix it together and it just kind of seeks its own level. But then there's also putty or like clay, Play-Doh. It's 2-part and you just kind of knead it and then you kind of pack it in and it holds its shape much better. So epoxy can be used to contour the ports. And with a flow bench, you can use modeling clay. And you can put the modeling clay in and you can see what happens on the flow bench, velocity zones with your velocity probe. And then when you find the shape that you like, replace the clay with actual epoxy. If you did nothing more than just go in and clean up the factory machine marks. Standard Abrasives did a small block Chevy, and that's all they did. They picked up 26 horsepower on a stock 4-barrel 350 pseudo-performance engine. The type of machine marks that you're going to find are going to be around the guides. There's a big boss around the guides, so you smooth that out for aerodynamics. And then undercuts, like around the valve seat. And if you look at the images, there's 2 examples where you're just trying to get rid of the crap that was left over from the machining process. The exhaust ports should be left relatively smooth. They're flowing dry, so you don't have to worry about keeping fuel in suspension. You just got to get the exhaust out. However, the intake ports need to be textured. Unless it's a GDI engine where the fuel is injected directly into the cylinder, if your head flows liquids in there, fuel, then the rougher the better. And on the left in that image, you'll see what I call power lines. And on the right, it's called scalloping. And scalloping is something that has been explored since, I want to say, the 1970s. So the power lines, I had some tools made up. And initially, just a 20 pitch, and I would go in and put 20 pitch threads in the intake ports. And then I got to thinking, well, wait a minute, rumble strips. The rumble strips on the side of the highway are spaced so that when you're doing 70 miles an hour, they get your attention. But if you were going over, say, 15, 20 miles an hour, it'd just be ba-bump, 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 ba-bump. And then you look at the rumble strips in a mall parking lot, and they're spaced so that at 20, 30 miles an hour, they get your attention. Well, maybe that would apply with the power lines as well. So I had the tools made up for 20, 16, and 12. So like a fine, medium, coarse pitch. And I found that with changing the pitch of the threads, the coarser would create a thicker boundary layer and push the velocity zone further away from the wall. And the thinner power lines didn't push as hard. So by using the different pitches, I could literally guide that velocity zone right exactly where I want it, so it hit the tangent and spin around.